Welcome back to Chem 4300. In this video, we're going to continue Chapter 8 on classical wave motion, and now we're going to look at a web app written by Paul Falstad that nicely illustrates waves on a circular membrane. Before I do that, however, I'm going to go back a bit here and review our results from the derivation of the normal modes on a circular membrane. And what we found was that normal modes are described by this equation here. And one of the things you'll notice is that there are indices here, integers m and n, which describe the different normal modes. And the normal modes depend upon this guy, which is the Bessel function of the first kind. And then it depends on the angular part here, which is either a cosine part or a sine part. And then there is the time dependence here, which we describe with this cosine time dependence. And what we learned is that these normal modes will have nodes in them. So for example, there are going to be n-1 radial nodes. So if I look here going down, this is n equals 1, n equals 2, n equals 3. So this one has 0 radial nodes. This one has 1 radial node, which goes around like this. 3 has 2 radial nodes, so the first one inside, the next one out here, and so on. We also find that there are m angular nodes, so depending on the value of m, so with m equal to 0, then we have no angular nodes, but with m equal to 1, then we have 1 angular node. So on this side, the amplitude is opposite sign of this side. And then here with m equals 2, we have 2 angular nodes, and m equals 3, we have 3 angular nodes, and so on. Now this illustration here is just for the case of cosine m phi, but if you do phi, the sine term, then that normal mode would look exactly like these, except they would be shifted 90 degrees. If you did a rotation 90 degrees around, then you would get what the sine normal modes look like. So what we're going to do by looking at the app is we're going to be able to see the actual time dependence and explore also how any shape on this membrane can be decomposed into these normal modes. So we'll be able to look at some kind of shape that's generated by, say, sort of striking the membrane and setting it into motion, and we can look at the decomposition of that wave, that arbitrary wave, in terms of the amplitudes of these different normal modes. So let's go now to the app. Okay, I'm going to make it a little bit bigger here. And the first thing I'm going to do is I'm going to adjust the view so that we can see both the 3D view and then a 2D view, which is just looking at it effectively from top down. And the color is going to tell us the sign of the wave function. So when it's green, it's positive, and when it's red, it's negative. I'm also going to increase the resolution here, and that will help later on. So right now what we're doing is looking at the fundamental, and so that's indicated here. This is very similar to what we had with the rectangular membrane, and what we see is that we have the fundamental moving, and I'm going to turn it off, so now it's back to its equilibrium position. When I move this direction, I'm going to be looking at different normal modes associated with increasing m values. Now there's a sine and a cosine in our normal mode, so one of these guys will excite the cosine, and the other one will excite the sine for a given value of m. So here we're looking at m equals 1, that's the sine, m equals 1, that's the cosine. So when I go here, that's m equals 2, that's the cosine, m equals 2, that's the sine. And you can see already, so for m equals 2, we see 1, 2 nodes. If I go back here, for m equals 1, we see the 1 node. If I move up, so this is m equals 1, 2, 3, 4, 5. If I look at the cosine of m equals 5, then you see here we should have 5 nodal lines, angular nodes in this wave function. Now I'll turn it off, and next I'll explore the wave function as we increase n, with keeping m equal to 0. So now this is n equals 1, and now I'm going to turn that off and do n equals 2. So now we have n equals 2, and you can see now there's a radial node here. So n equals 2 requires n-1 or 1 radial node, and that we see here. And if I change this to n equals 3, then we see the 2 radial nodes. and so on. So here you can see as I keep moving up, the number of radial nodes increasing as I increase n. Now, of course, you can also have increase m and n. So here I have the cosine part of m equals 1 and the n equal 2 normal mode. And so here we see that there is a one radial node, and then here we have one angular node, and this is what the wave function looks like for that normal mode. So you can go anywhere you want here to see the different normal modes, and yeah, they're kind of interesting to look at, of course. So the other interesting thing about this is we can adjust this app so that we can actually play a note, in a sense. We can hit this membrane like a drumstick and excite many different normal modes, and then you can watch how that pattern evolves with time. So the way I hit it, I created this particular pattern of normal modes, and as they evolve in time, this is what the shape looks like, which is kind of cool here. Let's do another stroke. I'm going to try to pull it right in the close to the middle here. If I can get it quite there. It's more like there we go. That's closer to the middle. And you can see how that wave function evolves in time and the decomposition of it in terms of the normal modes. So I'll let you, again, play with this yourself. There's a difference between poke and strike. So strike would be more like hitting it with a drumstick, I think. There. That would be a strike. And it's kind of fun to watch. And you can also, again, you can turn on the damping here, because a real drum head, for example, would eventually damp away. And to watch that damping occur, you probably need to increase the speed. And then you see all of these guys eventually disappearing. All right, well, I'll leave the rest of this for you to explore, but it does sort of nicely illustrate some of the equations that we derived in class, and gives you a nice 3D and time-dependent visualization of the circular membrane waves.